I'm going to be showing you how we can prove that the cosine rule is true. So, as a reminder, the cosine rule has two different formations, but we're only going to prove this first one because the second one is just a rearrangement of the first one. They're exactly the same. So we've got a squared equals b squared plus c squared minus 2bc cos a. And if I haven't made it clear yet, this is a formula that you have to know, you have to memorize. A squared equals b squared plus c squared minus 2bc cos a. And it's all built around this triangle with the capital letters in the angles and the little letters being opposite. Now you may remember for our proof of the area formula and our proof of the sine rule, we had to first split the triangle into something we knew more about, right angle triangles. So I'm once again going to draw a line right down the middle to turn this into two right angle triangles. Now for this one, we haven't needed to do this yet, but for this one we do need it. For the cosine rule, we do need to do this. I'm going to need to be considering these lengths at the bottom. Now we don't know what this length is. I don't know how this is split up C. I know that these two added together is C, but I don't know how long this one is. And as is generally true in algebra, when I don't know how long something is, I'm just going to give it a name. So I'm just going to call this length here y. So the length y is the length from this vertex to my right angle over here. Now I also want to know this length. I could just call this another letter, but actually I don't want to introduce another letter if I don't have to. And I just said that I know that this plus this has to be c, which means that this length is just c with y taken off it. So that length there is c minus y. So together this gives us length c, but actually I'm calling this one y and this one c minus y. And this now gives us two triangles that we can work with. Now we've already noticed that the cosine rule is very related to Pythagoras' theorem. So that's what I'm going to start by using. I'm going to use Pythagoras' theorem on both of these right angle triangles. And that's absolutely fine because they're right angle triangles. We can use Pythagoras' theorem with right angle triangles. So let's look at this first triangle. I can see that hypotenuse is b. The other two lengths are x and y. So that must mean that x squared plus y squared is b squared. That's just Pythagoras' theorem. The hypotenuse squared is equal to the two other sides squared. And add it together. We can do exactly the same thing with this other length here, this other triangle here, sorry. We've got a squared is going to be, well, x squared and c minus y squared. So I've just used Pythagoras' theorem on this second triangle. Now this is fine, but I'm going to rewrite this into being the same, in the same form. So I'm going to have x squared equals b squared minus y squared, and x squared equals a squared minus c minus y squared. Can you see how I've just rearranged both of these so that they're x squared equals instead of x squared plus, essentially. So for the first one I had to take away y squared from both sides, and for the second one I had to take away c minus y squared from both sides. That means that I can make these two things equal because they're both x squared, which means that b squared minus y squared is equal to a squared minus c minus y squared. Hopefully you can see that I've just, because these two are both x squared, I can say that they're both equal to each other. And what I've done there is I've eliminated x squared as a problem, which is going to be useful because that's one unknown that I now don't have. The other thing I still need to get rid of is this y, because there's no y in the cosine rule. Okay, now this next page is going to be a page that I love, but you may not, because it is essentially just a lot of algebra, a lot of rearranging. I've kept this on the side of the screen because these are the things that are in our head. This is the picture of the triangle we're describing, and this is the cosine rule that I'm aiming to get by the end of my proof. So we just agreed that b squared minus y squared is a squared minus c minus y squared. What I would quite like to do is I'd quite like to expand these brackets. So that's exactly what I'm going to do. I'm going to remember that c minus y squared is just c minus y times c minus y. That's just rewriting the exact same thing. And then I can expand those brackets So I'm going to do c times c times minus y times c, and minus y times minus y, which gives me that, c squared minus 2cy plus y squared. Now, I've left this in brackets for now, just because I'm very cautious about that minus sign at the beginning, because I know that I've got to have negative versions of all of these things. So actually, when I expand out the brackets properly, I end up with negative c squared, negative times negative, so I've got plus 2cy, and then we've got negative y squared. I just had to be very careful at that last step that I didn't make a sign mistake. Now, you'll notice that we've got this negative y squared, this take away y squared, appears at the end of both of these statements. So if I added y squared to both sides of the equation, I would get rid of that as a problem entirely. I'm going to add y squared to both sides. And now I've only got b squared equals a squared minus c squared plus 2cy. This is already starting to look quite a bit like this. So this is what's going to guide my next step. I want to have a squared equals instead of b squared equals. So what I'm going to have to do is I'm going to have to add on c squared to both sides, and then take away 2cy from both sides. So now I've got a squared equals b squared plus c squared minus 2cy, which is extremely close to a squared equals b squared plus c squared minus 2bc cos a. But somehow I need to change that y so that it's b cos a. Well, I can do that relatively easily. If I go back to my triangle, I'm clearly after cos somehow. I want to introduce cos into what we're doing. So I know that my cosine ratio is this. Cos of theta is equal to the adjacent over the hypotenuse. So cos of a here is going to be the adjacent, which is y, over the hypotenuse, which is b. So cos of a is equal to y over b. If I change this so that it says y equals, by timesing both sides by b, I get that y is b cos a, which is exactly what I wanted it to be. So if I finally just combine these last two things, so I said a couple of slides ago that b squared plus c squared minus 2cy is a squared, and I've just told you that y is b cos a, which means if I substitute that y value in, I get a squared equals b squared plus c squared minus 2bc cos a, which is the cosine rule. Okay, so the key points from this video. To prove the cosine rule for all triangles, we first need to cut up the triangle into two right-angled triangles, as we have done for all of these proofs. We can then use Pythagoras' theorem and K with these new triangles to prove the statement.